Alright, so today I'm going to be finishing the last Professor Leonard review video, and then we'll see how many sections of Paul's Online Math Notes I can finish today. Seven more of that, so this last one's only 15 minutes.
All right. Now the last bit of review, last section that we're going to cover in this class is 0.4. We're going to talk about how to combine some functions. I am not going to spend a whole lot of time on this, maybe 20, 25 minutes or so. We're going to go kind of quick on it. I just want to make some key points, show you a few things that we can do, and that's it.
So video 4, combining functions. Alright, let's see.
Combining functions. Really what I need you to know is that we can add, subtract, multiply, divide, and compose functions. That's really about it. What we mean by add, subtract, multiply, divide, if I give you these two functions like f of x equals this, and g of x is this, you need to know how to add, subtract, multiply, and divide them. It's not hard, it's not a big deal. If we want f plus g of x, what that means is we're just going to simply add the functions together, f of x.
So you do like 1 plus x minus 3 minus 2, I think. Should be x minus 5. I think that's it. Maybe?
Plus g of x. In our case, that means we'd have 1 plus square root of 2 minus x minus 2 plus x
Is that
minus
it?
3. You get rid of your...
So that's all you do, really. It's not like f plus... I guess the reason f times g of x is different is because well, that would be f of g of x, right? No, whatever. Okay, so you literally just add them. Alright, good to know. And then plus x minus 3. So negative 2 plus x plus square root of x minus 2.
Parentheses by distributing if you had to, and then combine some like terms. In our case, we should be getting negative 2 plus square root of x minus 2 plus x. Can you verify that that's the right answer? Yeah? Yes, okay. You should be able to do things like f minus g of x, which is basically the same thing except you have a minus in the middle. You have
So you got to
negative.
distribute it, yeah.
You've been doing this stuff since basic algebra, which is why we're not going to spend a whole lot of time on it. In our case, we'd have 1 plus square root of x minus 2 minus x minus 3. Notice, though, this is just a little different than the addition. With the addition, you can just drop parentheses because there's no negative to distribute. However, what happens to these sides? Those are definitely going to change. You guys see that they're going to change. Yes, no? That's going to be minus x and then the plus 3. Do you see the plus 3? So our answer, you can verify this later on your own. This is going to be 4 plus square root of x minus 2 minus x. If you did f of x times g of x, that's the same thing, only you're going to have to distribute. So in our case...
Okay, so saying this isn't the same as f of g of x. What do those look like again? Because this would be like if you're trying to find the intersection point, I'm pretty sure. That's when you use f of g of x, or g of f of x. Yeah, so f of g of 5, f of g of 5, yeah. So, yeah, a function composition, that's what it's called. So he's going to show that next. Maybe he'll explain, or he'll show how he writes it. What does function composition find? Not really give me an answer. Maybe he'll explain.
You get something like x plus x square root
I
of
think for that intersection point thing, I think I was thinking of system of equations.
x minus 2. Then you'd get
I'm not
minus
sure
3
function
minus 3
composition
square
really
root of
shows.
x minus 2. And there's nothing you can do to combine that. That would be it. Maybe factor that back out, but I mean, you'd be doing circular mathematics, so that's it. The only other thing we can do with our basic operations is f over g of x. In this case, we just put one function over the other in the appropriate order and make sure we have a new domain restriction. In our case right here, you knew that x could not be equal to 3. Are you guys seeing the 3? Also, one note that I do need to make, when you're doing these functions and they're asking you to find the domain, I'll write this out for you. The domain is the intersection of the domains of the original functions. You can't ever get rid of domain problems. All you can do is make more of them. Let me give you one example of that so that you see what I'm talking about. Let's say that I had this and this, and I asked you for this.
Well, it'd be x, but I guess the restrictions still apply to it, right?
Firstly, give me a little head nod if you're okay on how all these
So it can't be a negative number,
came about.
even though the square roots go away.
All right, that's pretty basic stuff. If you have the f times g of x, check this out. This would be the square root of x times the square root of x, yes, no? How much is the square root of x times the square root of x? Okay. So the question is, what's the domain? Is it all real numbers?
No.
Is it all real numbers? It looks like it, doesn't it? It looks like, oh, I can plug all those things in. But the idea...
I think it's that thing he was explaining before with if you change the functions, you can only create more problems. So like this is, you can't get rid of a problem, so the restrictions still apply, I think.
is, where did that come from?
Maybe.
What functions did it
But
come
also you're like manipulating them. So
from? Can you plug in all numbers to this? Can you plug in all numbers to that?
no.
Can you plug in negatives to either of those? And the problem is, even though it looks like it, you can't plug in negatives here.
Right.
Do you remember the idea with the whole? I introduced it to you a few days ago. I said, even though it looks like it was just x plus 2, looks like you should be able to plug in
Yeah, okay, that is what he's
x
talking
minus
about.
2, whatever it was. Looks like you should be able to plug in 2. You couldn't, right? Because the domain came from the original function before you simplified it. The same thing happens here. Make this note. When you're looking for a domain, the domain is actually the intersection. Intersection is what numbers are common to both functions. of the addition, subtraction, multiplication, or the division of those functions. So the domain is the intersection of the domains of the original functions. That's that symbol, that upside down U. Of the original functions. So for here, if you were asked to find the domain is not all real numbers. Heck no, even though it looks like it, the domain is not all real numbers. What the domain is numbers that are greater than or equal to 0. Why? Because that came from my original two functions. That's what those are coming from. How many people understand that? You can't just look at the final answer and give me a better domain. I said this, it was actually kind of a key point from a few days ago. I said, you can't ever make a domain better. All you can do is make more problems. That's all you can do by combining functions. We can't change the domain of this. All we can do is make it worse by doing this, right? That made it worse. You actually have a bigger problem here with that 3. You can't fix domain problems. All you can do is make them worse somehow. That sucks, but it's true. Does that make sense to you? You can't ever fix it. All right. The last thing we're going to talk about, we can also compose functions. This will be the last thing that we do. Just make sure that you know how to do compositions. I'll go really quickly through this. This is an intermediate algebra concept, so I'm going to make sure that you know it. What we mean by compositions is if I have f of x equals like x to the third minus 4, and g of x is the square root of x. We're basically just substituting in one function for another. So these two things, unless they're inverses, will have different answers. If they are inverses, their answer will both be x. That's how
Yeah, so you write it with like a whole type thing. I thought that was multiplication when I saw that first, but I guess it's written
tell
differently.
whether two functions are inverses or not. So f of g of x, I'll go through this one time. You make it f of g of x.
I know how to do
said
this,
the same
so
way. Then you start your
down.
substitution. You write f of, what is g of x? So we're going to write f of square root of x. What this says is you look at the function f. What's the function f right now? Read it out loud to me. X cubed minus 4. You all see that's x cubed minus 4? Let me kind of go back a little bit. I think I've lost some of you. What we're doing with compositions is inserting one function into another function. So how you start with it, the letters are in the same order here and here. F of g of x, f of g of x. Then we do a substitution. We actually do the composition. G of x becomes what g of x is. So g of x, we're writing square root of x. You with me on that? The only letter that's left that represents a function is the letter f. Agreed? So you go to that function. F says, what was it again? Everyone say it. Good. You say it again, and you're x cubed minus 4. X cubed minus 4, you get it? Then everywhere you said x, replace that word with the word parentheses. So instead of x cubed minus 4, you're going to do parentheses cubed minus 4. Do you get that? And that's what you write. You okay. F was x cubed minus 4. I'm going to write parentheses cubed minus 4. Parentheses cubed minus 4. You okay with that so far? Whatever was in this parentheses now goes in that parentheses. And that is your composition. That's as easy as that. Okay, we can do it that way for every composition you have. The other way, you would have g of f of x. That is g of, well, f of x is x cubed minus 4. The only letter that represents a function is g. I look at the g, it says square root of x. So I think square root of x, square root of x, square root of parentheses. Someone write square root of parentheses. Why? Because G said square root of parentheses right there. What goes in this parentheses? What goes in that parentheses? Whatever was in this one. Yeah. And that's how you do your composition. How many feel okay with the composition? That's a real fast way to do it. The last compositions that we need to talk about in the last 5 minutes or so. You should be able to do like multiple compositions as well. So for instance, if I say something crazy, like you got 3 functions, compose all of them, you should be able to do that. So let's say that we had like f's the square root of x. G is 1 over x. H is x cubed. Can you do
That does not look good. Anyway. So, I've never seen 3 of these like that. So, I could try. So, so we got square root of x, f of g, 1 over x, 1 over x cubed. I think that's it. Rewrite this. No. I think this is it.
They used to call them Fog and Goff, right? Can you do Foggo? Haha. Can you do that one? F of G of H? What do you think? Yeah. Why don't you try it on your own and see if you come with the same thing I get? I'm going to spend about 30 seconds doing it. So see if you get it. And I'm going to do it real nice and slow up on the board. Okay, try it. Let's see. F of G of H of X. Oh my. Well, that's f of g of x cubed, because that's h of x. All right, I got that. Now I continue looking on the inside of my parentheses. G says 1 over x, true? So this says f of, g said 1 over x, that's 1 over parentheses. 1 over parentheses, that would be 1 over x cubed. You see where the x cubed is coming from? Okay. Now it's the only letter that represents a function left is f. So f says square root of x. So I'm going to say, okay, square root of x, that's square root of parentheses. Square root of parentheses is 1 over x cubed. Or if you want to be fancy about it, the square root of 1 is 1. X, that's to the 1/2 power, so that would be the square root of x cubed like this. Do you agree? And you can write that as as 1 over x to the 3/2 power. Remember those fractional exponents, power over root? You can do that. Now, if I asked you for this question, can you find f of g of h of 8? Can you do that?
Just be 8 over 8 x 3/2.
What's that mean to do? Yeah.
Oh, you plug it in. Oh, crap. So you just, you plug it in the x.
You already did, right? You already have that on the board. Now can you plug in 8? Plug in 8, you're going to get 1 over 8 to the 3/2. By the way, the easy way to do that.
So you could rewrite that as, what is it? What's it? Square root of 8. 4, so 2 squared, so 2. Like that or something?
These without a calculator, take, oh wait, did I give you the wrong one? No, I didn't, that's fine. I guess you would do it. Just plug in your calculator. What do you get out of that? 2 to the 3 halves.
Our calculators are moving.
One over. Is it a decimal? Okay, well, leave it 1 over 8 to the 3 halves for now. If it's something like a 4, you could have taken a square root and then cubed it. You would have gotten like
64.
the last thing we're going to talk about. Oh, yeah, 30 seconds, perfect. You should be able to also go backwards. For instance, if I had given you something like h of x equals x minus 7 cubed, can you write that as a composition f of g of x? Can you write that as a composition? For instance, can you define the inside part as one function, the outside part as another function, and write it appropriately so that when you compose them, it gives you that?
I'm not
The
sure.
answer is always yeah.
What do you mean?
Pick the inside part as a trivial function x, or I'm sorry, you pick the inside part as one function, and then you always have like x to the third. So for instance, in our case, I would say f of x would be x to the third. That's the outside part. Remember how we said parentheses to the what x was parentheses? Whenever you see the parentheses, just treat that like an x. That's x to the third, and then g of x would be the inside part. And that would be I'm sorry, something like h of x equals x minus 7 cubed. Can you write that as a composition f of g of x? Can you write that as a composition? For instance, can you define the inside part as one function, the outside part as another function, and write it appropriately so that when you compose them, it gives you that? The answer is always yeah. You pick the inside part as a trivial function x, or I'm sorry, you pick the inside part as one function, and then you always have like x to the third. So for instance, in our case, I would say f of x would be x to the third. That's the outside part. Remember how we said parentheses what x was parentheses? Whenever you see the parentheses, just treat that like an x. That's x to the third, and then g of x would be the inside part. And that would be your composition. So we should be able to go back.
Crap. What? So yeah, if you did, okay. Oh, okay. I definitely see what he means. So you turn that x into a parentheses, x minus 7 cube. Okay. Okay, that makes a lot of sense.
Well, how many feel okay with what we talked about? Good deal. So let's get.
Limits. Still gotta do pause on the math notes. So. This is probably his most popular video, right? Yeah. That's probably when it gets fun for sure. Alright, let's see. So next we got solving trig equations. In this section we will take a look at solving trig equations. This is something that you will be asked to do on a fairly regular basis in many classes. Let's just jump into the examples and see how to solve trig equations. Solve 2 cos t equals square root of 3. Divide by 2 cos t equals square root of 3 over 2. We could do inverse, or we could just unit circle. If we look on the unit circle, square root of 3 over 2 is pi over 6 in radians. Where else is, it's also 11 pi over 6 And I think that's it. Yeah. So I think there's two answers that they can use here. So let's see what Paul does. There's really not a whole lot to do in solving this kind of trig equation. We first need to get the trig function on one side by itself. To do this, all we need to do is divide both sides by 2. Okay, on the right track. We are looking for values of t, for which cosine will have a value of square root of 3 over 2. So let's take a look at the following unit circle. Yep. From a quick inspection, we can see that t equals pi over 6 is a solution. However, as we've shown on the unit circle, there is another angle, which will also be a solution. We need to determine what that angle is. When we look for these angles, we typically want positive angles that lie between 0 and 2 pi. This angle will not, oh wait, you could rewrite this as plus 2 pi n, plus 2 pi n, since you can rotate around infinitely many times. So this angle would not be the only possibility, of course, but we typically look for angles that meet these conditions. To find this angle for this problem, all we need to do is use a little geometry. The angle in the first quadrant makes an angle of pi over 6 with the positive x-axis. Then so must the angle in the fourth quadrant, so we have two options. All students take calculus. Okay, so cosine is positive in here, and that's why, yeah. So that's how you'd figure that out. So we have two options. We could use negative pi over 6, but again, it's more common to use positive angles. To get a positive angle, all we need to do is use the fact that the angle is pi over 6 with the positive x-axis, as noted above. And a positive angle will be t, 2 pi minus pi over 6 equals 11 pi over 6. One way to remember how to get the positive form of the second angle is to think of making one full revolution from the x-axis, i.e. 2 pi, and then backing off, subtracting pi over 6. We aren't done with this problem. As the discussion about finding the second angle has shown, there are many ways to write any given angle on the unit circle. Sometimes it will be negative pi over 6 that we want for the solution, and sometimes we will want both, or neither of the listed angles. Therefore, since there isn't anything in this problem, contrast this with the next problem. To tell us which is the correct solution, we will need to list all possible solutions. This is very easy to do. Recall from the previous section, and you'll see there that we used pi over 6 plus 2 pi n. I think that's what yeah, and then he wrote the definition of n, but I'm not. To represent all the possible angles that can end at the same location on the unit circle, i.e. angles that end at pi over 6, remember that all this says is that we start at pi over 6, then rotate around in the counterclockwise direction, n is positive, or clockwise direction, n is negative. For n complete rotations, the same thing can be done for the second solution. So altogether, the complete solution to this problem is pi over 6 plus 2 pi n, 11 pi over 6 plus 2 pi n. Alright. As a final thought, notice that we can get negative pi over 6 by using negative 1 in the second solution. Now in a calculus class, this is not a typical trig equation that we'll be asked to solve. A more typical example is the next one. Okay. I'll be right back then. And then, how long have I been streaming? 30 minutes? Oh, okay. I could probably get all the reviews sections done today and Paul's. We'll see how it goes. Okay, so the next example is the exact same thing, but it says on negative 2 pi, 2 pi. So it seems like wants us to list everything in one rotation, right? So it would be cos of t equals square root of 3 over 2, 11 pi over 6, plus or minus. But I could be wrong because I haven't really seen this written like this ever before. So in a calculus class, we are more often interested in only the solutions to our trig equation that fall in a certain interval. The first step in this kind of problem is to find all the possible solutions. We did this in the previous example. Now to find the solutions in the interval, all we need to do is start picking values of n, plugging them in, and getting the solutions that will fall into the interval that we've been given. Pi over 6 plus 2 pi of 0, pi over 6 is less than 2 pi. 11 pi over 6 plus 2 pi is 0, 11 pi over 6 is less than 2 pi. Now notice that if we take any positive value of n, it will be adding on multiples of 2 pi onto a positive quantity, and this will take us past the upper bound of our interval, so we don't need to take any positive value of n. However, just because we aren't going to take any positive value of n doesn't mean that we shouldn't ask. Also look at the negative values of n. N equals -1, and it just equals the negative version. So these are both greater than -2 pi, and so are solutions, but if we subtract another 2 pi off, then once again we'll be outside the interval, so we found all the possible solutions that lie inside the interval. Alright, so let's see if you've got this all down. Solve 2 sine, or wait. Example 2. Example 1. I guess I should label this as Paul's online math notes section. What is this? 1.4. Solving trig equations. Alright, so example 3. We got sine of 2x equals negative cos of 2x on negative 3 pi over 2, 3 pi over 2. Okay, now what is going on here? So trig identities list. Let's get the first 15. And this is 22. Good enough. So okay, so sine 2x equals 2 times sine x times cos x. So I don't know if we want to write it like that, or 2 times sine x times cos x equals wait, what's that? Negative cos. Can you do that? Negative cos 2x? No, that's only, okay, you can do that. It's only whenever it's a negative angle, it equals a positive. Okay. So it can be on the outside. So negative What's cos 2x? Can be cos squared x minus sine squared x, 2 cos squared x minus 1, or 1 minus 2 sine squared x. Yeah, I'm not seeing like anything, so I just want to look at the example, to be honest. This problem is very similar to the other problems in the section with a very important difference. We'll start this problem exactly the same way as we did in the first example. So first get sine on one side by itself. Okay. Wait, did I write this down right? Wait, which example? Wait, what? What was I writing down? 2 sine 5 of x equals negative. What world am I living in right now? What? How did I even get this? Okay, I must be just making up stuff, cause like what? Anyway, so the example is 2 sine 5 of x, 5x equals negative square root of 3. Okay, pasted. Divide by 2. Sine 5x equals negative square root of 3 over 2. If we look for negative square root of 3 over 2 in the unit circle, and the y, got here and here. So it could be 4 pi over 3 or it could be 5 pi over 3. Okay, that could be rewritten as divided by 5. So we got 5 pi over 15 for this, or 4 pi over 15 for this. Can you rewrite this as pi over 3? Maybe. Well, if you can, it'd be negative, because this is, or wait. Okay, the one that I wrote down is example 4. Does that make sense? It's between negative pi and 2 pi, not negative 2 pi. So, let's see, if you plugged in n plus 2 pi n, wait, it would be plus pi n, right? So then negative 1, if you plug in a negative 1, you get 3 pi over 3 plus pi over 3, 4 pi over 3, and then for this plus pi n negative 1 if you plug that in, or wait, negative 4 pi over 3, subtracting, or no, okay, pi over 3 minus pi n, pi over 3 minus 3 pi, negative 2 pi over 3. So we got pi over 3, negative 2 pi over 3. 4 pi over 15 minus 15 pi over 15, negative 11 pi over 15. And what's the original? 4 pi over 15. Yeah, so I could be way off here, but that's the sets I'm getting. So this problem is very similar to the other problems in this section with a very important difference. We'll start this problem in exactly the same way as we did the first example. So first get the sign on one side by itself. Okay, I did that. So you get negative square root of 3 over 2. We are looking for angles that will give negative square root of 3 over 2 on the sine function. Let's go to our trusty unit circle. Now there are there are no angles in the first quadrant, for which sine has a value of negative square root of 3 over 2. However, there are 2 angles in the lower half of the unit circle, for which sine will have the value of negative square root of 3 over 2. So what are these angles? Notice that sine pi over 3 equals equals square root of 3 over 2. Given this, we now know that the angle in the third quadrant will be pi over 3 below the negative x-axis, or pi plus square root of pi plus pi over 3 equals 4 pi over 3. Okay, wait. Okay. Oh, he's explaining how he gets his answer just from looking at the first quadrant. Okay. So, yeah, then you know the negative version of that is 4 pi over 3, because you're adding pi. An easy way to remember this is notice that we'll rotate half a revolution from the positive x-axis to the negative x-axis, and then add on pi over 3 to reach the angle we are looking for. Likewise, the angle in the fourth quadrant will pi over 3 below the positive x-axis. So we could use negative pi over 3, or 2 pi minus pi over 3 equals 5 pi over 3. Remember that we are typically looking for positive angles between 0 and 2 pi. So we'll use the positive angle. An easy way to remember how to the positive angle, I don't know what that means. Here is to rotate one full revolution from the positive x-axis, i.e. 2 pi, and then backing off, i.e. subtracting pi over 3. Now we come to the very important difference between this problem and the previous problems in this section. The solution is not 4 pi over 3 plus 2 pi n, blah blah blah, x equals 5 pi over 3 plus 2 pi n, so that's not it. This is not the set of solutions because we are not looking for the values of x, for which sine x equals negative square root of 3 over 2, but instead we are looking for values for which sine 5 of x equals negative square root of 3 over 2. Notice the difference in the arguments of the sine function. One is x, one is 5 over x, 5 times x. This makes all the difference in the world, jeez dude, in finding the solution. Therefore, the set of solutions is 5x equals 4 pi over 3 plus 2 pi n. Well, actually, it's not the solution. Looking for the values of x, so divide everything by 5. Okay. So 4 pi over 15 plus 2 pi n. Okay, I see that. Notice that we also divided 2 pi n by 5 as well. This is important. If we don't do that, you will miss solutions, okay? So then he sets n equal to 1. we'll leave it to you to verify our work showing this they are solutions. However, it makes the point. If you don't divide by the 2 pi n by 5, you would have missed these solutions. Okay. Okay, now that we've gotten all possible solutions, it's time to find the solutions on the given interval. We'll do this as we did in the previous problem, pick the values of n to get solutions. Whoa. Okay, so we finally got past the right endpoint of our interval, so we don't need any more positive n. Really? Okay. Jeez, dude. That's all of them? Are you kidding? Okay. So I'll restart this. So I was right to divide it by 5, but I also gotta divide plus 2 pi over n plus 2 pi over n. Or wait, plus 2 pi over n plus 2 pi n plus 2 pi n plus 2 pi n. And then divide by 5. So 4 pi over 15 plus 2 pi n over 5. 5 pi over 15 plus 2 pi n over 5. So you can't simplify 5 pi over 15 then, can you? Or no, you can, okay. So he does simplify it. So I was right to do that. Pi over 3 plus 2 pi n over 5. Okay. Alright, now I start plugging in stuff. So x equals 4 pi over 15 plus 2 pi 1 over 5. So you get x equals 4 pi over 15 plus 2 pi over 5. So 6 pi over 15 plus 4 pi over 15. It's 10 pi over 15. Which can be simplified as x equals 2 pi over 3, which is less than 2 pi. So I'll circle that. That's one of the solutions. X equals 4 pi over 15 plus 2 pi 2 over 5. X equals 4 pi over 15 plus 4 pi over 5. So you get 12 pi over 15 plus 4 pi. I'm not going to keep writing x equals. So 16 pi over 15. Pi over 15. Well, 16 over 15 is definitely not 2. or greater than 2. I'll just be safe. 16 by 15 is 1.06 something, so that's less than 2 pi. So this is one of the answers. X equals 4 pi over 15 plus 2 pi 3 over 5. Whoops, I'm on the... okay. So 6 pi over 5 plus 4 pi over 15. So 18 pi over 15 plus 4 pi over 15. 22 pi over 15. 22 divided by 15 is 1.46 something. So it's less than 2 pi. It's one of the solutions. X equals 4 pi over 15 plus 2 pi 4 over 5. So that's 8 pi over 5 plus 4 pi over 15. Gonna have to do 24 pi over 15 plus 4 pi over 15. So 29 pi over 15. That's less than 2 pi, probably. 1.9 something, so. Then the next one should be over the limit. 4 pi over 15. That's 2 pi 5 over 5. So 10 pi over 5 plus 4 pi over 15. We got 30 pi over 15 plus 4 pi over 15. 34 pi over 15. 34 divided by 15, and that's over 2, so it's not less than 2 pi. And let's see. So x does not equal 34 pi over 15. See if I'm on the right track. 30, wait, he's 35. Oh, because he's doing them all at the same time, okay. I was just doing the 4 pi over 15 first, so now I gotta do, these are long. X equals pi over 3. Pi over 3 plus 2 pi 1 over 5. So 2 pi over 5 plus pi over 3. We got 5 pi over 15 plus 6 pi over 15, 11 pi over 15, it's less than 2 pi n. X equals pi over 3 plus 2 pi 2 over 5. So 5 pi over 15 plus 4 pi over 5. 5 pi over 15 plus 12 pi over 15, 17 pi over 15. It's less than 2 pi. Oh, I put n up here. So that's less than 2 pi. X equals pi over 3 plus 2 pi 3 over 5. So 5 pi over 15 plus 6 pi over 5. 18 pi over 15 plus 5 pi over 15. 23 pi over 15. It's less than 2 pi. Yeah, so it's one of the solutions. X equals pi over 3 plus 2 pi 4 over 5. It's less than 2 pi. So, or wait, don't have to put that yet. So 5 pi over 15 plus 8 pi over 5. 5 pi over 15 plus 24 pi over 15. 29 pi over 15 is less than 2 pi. It's an answer. The last one shouldn't be an answer. Pi over 3 plus 2 pi 5 over 5. 10 pi over 5 plus 5 pi over 15. 30 pi over 15 plus 5 pi over 15. 35 pi over 15. And that's more than 2, so it's not less than 2 pi. X does not equal that. Okay. So these are all the solutions for now. That is a lot of writing, jeez. So now I gotta say X equals 4 pi over 15 plus 2 pi negative 1 over 5 has to be less than, what is it? Less than negative pi. So negative 2 pi over 5 plus, I guess, crap, negative 2 pi over 5, 4 pi over 15, 4 pi over 15 minus 6 pi over 15, negative 2 pi over 15. That's less than negative pi, so it works. So 4 pi over 15 plus 2 pi negative 2 over 5, negative 4 pi over 5, 4 pi over 15, 4 pi over 15 minus 412 pi over 15, negative 8 pi over 15, so less than negative pi. So that's one of the solutions. X equals negative 2 pi over 15, no, 4 pi over 15 plus 2 pi negative 3 over 5, should be less than negative pi, I'm not gonna write that. Negative 6 pi over 5 plus 4 pi over 15. 4 pi over 15 minus 18 pi over 15 So that's negative 14 pi over 15 less than negative pi. Works. 4 pi over 15 plus 2 pi negative 4 over 5. 4 pi over 15 plus negative 8 pi over 5, 4 pi over 15 minus negative 24 pi over 15. Negative 20 pi over 15 is not less than 2, or not less than negative pi. So that's one of the solutions, or not one of the solutions. It's not equal that. X equals pi over 3 plus 2 pi negative 1 over 5. X equals 3 pi over 15 plus negative 2 pi over 5. X equals 3 pi over 15 minus 6 pi over 15. X equals negative 3 pi over 15, and that's less than negative pi, so it works. X equals 3 pi over 15 minus 2 pi negative 2 over 5. 3 pi over 15 minus, or wait, it's not minus, it's plus. Minus 4 pi over 5. 3 pi over 15 minus 12 pi over 15. Negative 9 pi over 15 is less than 2 pi, or less than negative pi, so it works. X equals 3 pi over 15 plus 2 pi negative 3 over 5. X equals 3 pi over 15 minus 6 pi over 5. So we got 3 pi over 15 minus 18 pi over 15 negative 15 pi over 15. It's not less than negative pi, because it is negative pi, so it doesn't work. Alright, let me make sure on that last one. So whenever they plugged it in, negative 6, negative 18, wait a minute, it should be 5 pi over 15. Are you kidding me? Did I do this all wrong? Yeah, there should be 5 pi. When did I start writing 3 pi? So negative 13 pi over 15. You can keep going. That's annoying. Um, 5 pi over 15 minus 18, or minus 2 pi negative 4 over 5 plus 5 pi over 15 minus 8 pi over 5 negative 24 pi over 5, 5 pi over 15 negative 19 pi over 15. It's not less than negative pi. X does not equal this. Okay. So this does equal, or this is less than negative pi right here. So this is one of them. Alright, this is wrong. I'm not gonna change all the 3's. It's just gonna be dumb. Negative 7 pi for 15. You know what, I'll just like, there. So this is negative pi over 15. Okay, I did write 5 pi over 15 up here. So I don't know when that started happening. I started writing 3 pi. Let's check. Okay, that's a lot of solutions. So the first one, 2 pi over 3. Well, the first solution's 4 pi over 15 and then pi over 3. Can I find those? 4 pi over 15, pi over 3. 2 pi over 3. 16 pi over 15. 22 pi over 15. 29 pi over 15. 11 pi over 15. 17 pi over 15. 23 pi over 15. 29 pi over 15. Negative 2 pi over 15. Negative 8 pi over 15. Negative 14 pi over 15. Negative pi over 15. Negative 7 pi over 15. Negative 13 pi over 15. That should be it. Okay. So, I don't think I had to do all that work, but I think I got the picture after like the second problem, but you know it happens. So basically what you do, you divide by the 2 like the last 2, then you divide by 5 to get your first 2 answers, but you also got to divide 5 by the plus 2 pi n, and then you just start plugging in stuff, and yeah. So example 4 is next. Let's work another example. Solve sine 2x. This is the one that I had no idea how to do. Like, actually no clue. Sine 2x equals negative cos 2x on negative 3 pi over 2, 3 pi over 2. So I tried using the double angle formula thing. I think that's what it's called. Anywhere it says that. I don't know, but yeah, I don't know how to, like, I don't know. So let's see. This problem is a little different from the previous ones. First, we need to do some rearranging and simplification. Okay. So let me go with that then. So to divide the cos 2x over sine 2x for cos 2x equal to negative 1. So I get tan 2x equals to negative 1. Is that what they get? Yeah. Can I do it from here? Let's see. I didn't think of this as a -1. So yeah, I can see how they did that. To pull up a new page now. Okay. So we have tan 2x equals -1. So from here I think I can do it. So tan equals -1. Quadrant 2 here. So say 2x equals 3 pi over 4 plus 2 pi n. We could say what website is this? I don't even know. Or else is it negative? Not down here. Down here. So 7 pi over 4 plus 2 pi n. So from here we divide. I'll move this down. And I'll circle this so I remember the first two solutions. Or wait, no, these aren't the first two solutions. We gotta divide by 2 still. So 2, crap. Divide by 2. So x equals 3 over 1. 3 pi over 8 plus pi n. X equals 3 pi, or wait, I'm not writing. 7 pi over 8 plus pi n. Okay, so move this. And now we circle 3 pi over 8 and the 7 pi over 8. So now x equals 3 pi over 8 plus pi. And what are we trying to stay in between? 3 pi over, negative 3 pi over 2, 3 pi over 2. So plug in, what is, that's 1.5. So alright, let's keep that in mind. Plug in a 1. So 3 pi over 8 plus pi, 3 pi over 8, plus 8 pi over 8. So we got 11 pi over 8. I don't think that's over 1.5. Yeah, so that is less than 3 pi over 2. Let me just double check. It's 3 pi over 2, yeah. So that's one of the answers. I'll probably go over on the second one. X equals 3 pi over 8 plus pi 2. So 2 pi plus 3 pi over 8. We got 16 pi over 8 plus 3 pi over 8. 19 pi over 8. Sounds like it's over. Actually, it's definitely over because that's over 2. So I'll just look it up just for funsies. Yeah, it's over 2. So it's not less than 3 pi over 2. X does not equal this. Okay. Now I gotta check the other solution. That's what we say this was. I was checking 7 pi? No, 3 pi over 8. That's the first one I did. Now I'll do 7 pi over 8 plus pi n. So x equals 7 pi over 8 plus pi 1. 7 pi over 8 plus 8 pi over 8. We got 15 pi over 8. It's less than 3 pi over 2. I don't know, is it actually? 15 divided by 8. No. Yeah, so did I do this right? I don't think this is the answer. This is an answer you can use. So I'll move on. The original x equals 3. What's the original? X equals 3 pi over 8 plus pi n. So 3 pi over 8 plus pi negative 1. 3 pi over 8 minus pi. 3 pi over 8 minus 8 pi over 8. Minus 5 pi over 8. Negative 3 pi over 2. Yeah, it is, so it's an answer. Let's see. X equals 3 pi over 8 plus pi negative 2. X equals 3 pi over 8 minus 2 pi. 3 pi over 8 minus 16 pi over 8 minus 13 pi over 8. 13 over 8 is more than 1.5. So this is not less than 2, what are we, negative 3 pi over 2. X does not equal this. Move on to the other one. X equals 7 pi over 8. That is it, right? Yeah, plus pi negative 1. X equals 7 pi over 8 minus pi. X equals 7 pi over 8 minus 8 pi over 8. We got negative pi over 8. And that's less than 3 pi over 2, negative 3 pi over 2. Or wait. It has to be greater than, right? I was writing it wrong the whole time. It has to be greater than. I read it wrong on the other page too, but I'm definitely not going back, so I'll change it here, I guess. It's kind of annoying. I just realized that now. doesn't really change the answer, but it's not technically right, I guess. Alright, that's not a negative one. Okay, so from here I'm right. So this is one of the answers. 7 pi over 8 minus pi, or plus pi negative 2. 7 pi over 8 minus 2 pi for 1. 7 pi over 8 minus 16 pi over 8. 16 minus 7, I can't do that in my head because I'm not smart. Negative pi over 8. Negative 9 pi over 8. That's definitely not more than 1.5, but let me make sure. Yeah. Is greater than negative 3 pi over 2. Okay, so it's one of the solutions. Next one should go over x equals 7 pi over 8 plus 2, no, just pi, negative 3, 7 pi over 8 minus 3 pi over 1. We got 7 pi over 8 minus 24 pi over 8. Negative 17 pi over 8. Cannot get that mental math going today. It's greater than, well, it's definitely, no, it's not greater than, what is it? Negative 3 pi over 2. So it doesn't equal x. Okay. So let's check. Where does this even start? All the way up here. Okay. Wait, he like barely did anything. What are his solutions? Hold on. Let's start from the beginning. Okay. So you got tan 2x equals negative 1. So solving sine 2x, negative cos 2x, it's the same as solving tan 2x negative 1. Hopefully you'll recall this, that the smallest positive angle where a tangent is negative 1 is 3 pi over 4, and this is in the second quadrant. There's also a second angle for which tangent will be negative 1. Use a unit circle to illustrate this. So I did get 3 pi over 4 and wait a minute. I was using 7 pi. Okay, I was using 7 pi over 8. Okay. Okay, as shown in this unit circle, if we add pi to our first angle, we get 3 pi over 4 plus pi equals 7 pi over 4. And we get an angle that is in the fourth quadrant and has the same coordinates except for opposite signs. This means that tangent will also have a value of negative 1 here, and so is a second angle. This will always be true when solving tangent equations. Once we have one angle that will solve the equation, a second angle will always be pi plus the first angle. All possible angles are then 2x equals 3 pi over 4 plus 2 pi n, blah blah blah. Or upon dividing by 2, we get 3 pi over 4. Oh wait, I could have simplified this. Or wait, did I just do it wrong? No, I did it wrong. Yeah, what? Should this have been 14? Are you kidding me? Wait. Hold up. Wait. No, I got it right. What was I looking at? 14? Was it down here or something? Actually, what was I looking at there? Cause that's okay. I don't know. So 3 pi over 8, 7 pi over 8. Plus pi n. Yeah. Now let's determine solutions. Oh, I forgot to put in 0. Crap, I gotta remember that. I'll do that at the end here then. So we got 3 pi over 8 plus pi 0. 3 pi over 8 plus 8 pi over 8. Or wait, no. That's 1. Wait, no, okay, that's just the answer. Okay, never mind. That's just the, you don't have to divide by, or multiply by 0. Because I already got those. Anyway. Yeah, 3 pi over 8 is less than 3 pi over 2. 7 pi over 8 is less than 3 pi over 2. So for 1, it's 11 pi over 8. 15. Wait. Alright, mine would be more down here. Maybe, no? Oh. One wrong here. Oh, 50 pi over 8 is greater than, so that's not a solution. So I'm right with that. Unlike the previous example, only one of these will be in the interval. This will happen occasionally, so don't always expect both answers from a particular end to work. Also, we should now check n equals 2 for the first to see if it will be in or out of the interval. I'll leave it to you to check out that it's out of the interval. Okay, well I did check that, so. Where's the next? This is the next solution. Now let's check negative n, negative 5 pi over 8. And negative pi over 8 I should have gone, yeah. This one went over. She got negative 9 pi over 8, yep. So solution to negative 9 pi over 8, negative 5 pi over 8, negative pi over 8, 11 pi over 8, 7 pi over 8, 3 pi over 8. Okay, so the solution set at the bottom there, I think I was like confused because it was like backwards. Because I think in the first one he had it like in order, but whatever. Before moving on, we need to address one issue about the previous example. The solution method used there is not the standard solution method. Really. Because the second angle is just pi plus the first, and if we added pi onto the second angle, we'd be back at the line. Wait. Because the second angle is just pi plus the first, and if we added pi onto the second angle, we'd be back at the line representing the first angle. The more standard solution method is just to add pi n onto the first angle to get, then divided by 2 to get the full set of solutions. This set of solutions is identical to, 3 pi over 8. That's just one of them. Pi over n divided by 2. Oh. Okay, I mean, I guess. This set of solutions is identical to the set of solutions we got in the example. We'll leave it to you to plug in some n's and verify that. That's funny. So why did we not use the method in the previous example? Simple, the method in the previous example more closely mirrors the solution for cosine and sine. They both generally give 2 sets of angles, so for students that aren't comfortable with solving trig equations, it gives a consistent solution method. True, and I'm going to keep using it. Let's work on one more example so that we can make a point that needs to be understood when solving some trig equations. Paul's making a point over here. That means it's going to be long. Or maybe not, hopefully not. So we got cos 3x equals 2. 2, huh? 2. I don't get it. Yeah, I don't understand how to even start this, so this example is designed to remind you of certain properties about sine and cosine. Recall that -1 is less than or equal to cosine of theta less than or equal to -1, or normal 1, positive, and -1, blah blah blah. Therefore, since cosine can never be greater than 1, it definitely can't be 2. There are no solutions. Let's go. This is example 5. No solutions. Okay, that makes sense, because this is based off of the unit circle. It's important to remember that not all trig equations will have solutions. True. In this section, we solve some simple trig equations. There are more complicated trig equations that we can solve, so don't leave this section with the feeling that there's nothing harder out there in the world to solve. In fact, we'll see at least one of the more complicated problems in the next section. Nice. Also, every one of these problems came down to solutions involving one of the common or standard angles. Most trig equations won't come down to one of those, and will in fact need a calculator to solve. The next section is devoted to this kind of problem. Oh no. Alright. Let's keep going. 1, 2, 3, 4. We were just on 4, right? Yeah. 5. Let's move along, buddy. Part 1. There's 2 parts to this section. Paul's Online Math Notes. Section 1.5. Trig equations with calc. Part 1. So, section 1.5, solving trig equations with calculators, part 1. In the previous section, we started solving trig equations. The only problem with the equations we solved in there is that they pretty much all had solutions that came from a handful of standard angles. And of course, there are many equations out there that simply don't. Good to know. So in this section, we are going to take a look at some more trig equations, the majority of which will require the use of a calculator to solve. A couple won't need a calculator. The fact that we are using calculators in this section does not mean, however, that the problems in the previous section aren't important. It is going to be assumed in this section that the basics of solving trig equations are known, that we don't have to go back over them here. In particular, it is assumed that you can use a unit circle to help you find all answers to the equation. Although the process here is a little different, as we'll see, and it is assumed that you can find answers in a given interval. If you're unfamiliar with these ideas, you should first go to the previous section and go over those problems. Did that already. Before proceeding with the problems, we need to go over how our calculators work, so we can get the correct answers. Calculators are great tools, but if you don't know how they work and how to interpret their answers, you can get in serious trouble. First, as already pointed out in the previous sections, everything we are going to be doing here will be in radians, so make sure that your calculator is set to radians before attempting the problems in this section. Also, we are going to use 4 decimal places of accuracy in the work here. You can use more if you want, but in this class, we'll always use at least 4 decimal places of 4. I thought I used 3 in my class. I thought that was a lot. 4 is kind of crazy. You can use more if you want. That's crazy. Okay, use at least 4 decimal places of accuracy. Next, and somewhat more importantly, we need to understand how calculators give answers to inverse trig functions. We didn't cover inverse trig functions in this review, but they're just inverse functions, and we have talked a little bit about inverse functions in a review section. The only real difference is that we are now using trig functions. We'll only be looking at 3 of them, and they are inverse cosine, inverse sine, inverse tangent. As shown, there are 2 different notations that are commonly used, and these notes will be using the first form since it is a little more compact. Most calculators these days will have buttons on them for these three, so make sure that yours does as well. We now need to deal with how calculators give answers to these. Let's suppose, for example, we wanted our calculator to compute inverse cosine 3/4. What would that be? Well, I don't know. It's not in the unit circle, so. At least I don't think it is, right? There's no, yeah. So that would be like you're plugging in the coordinate thingy, the value, and you're getting a degree in radians. So he got 0.7227. So from the previous section, we know that there should be, in fact, an infinite number of answers to this. Yeah. I'm guessing this is between, what would this be between even? Couldn't there be another? No, okay, there's only one answer within one rotation, right? For this. Because you're putting in a... Or no, I got it mixed up. I think you're putting in the degree first? No. No, I didn't get mixed up. Okay. I should stop thinking. So... Infinite numbers of this answering this including a second angle that is in the intervals 0 to pi. However, our calculator only gave us a single answer. How to determine what the other angles are will be covered in the following examples, so we won't go into detail here about that. Okay. We need to point out, however, that the calculators will only give a single answer. And we're gonna have more work to do than just plugging a number into a calculator. Unfortunate for me. Since we know that there are supposed to be an infinite number of solutions to cos x equals 3/4, the next question we should ask then is just how did the calculator decide the return answer that it did? I'd like to know that too, actually. Why this one and not one of the others? Well, it gives the same answer every time. There are rules that determine just what answer the calculator gives when computing inverse trig functions. All calculators will give answers in the following ranges. So we got between 0 and pi. That's for the cos. For the sine, it's between negative pi 2 and pi 2. Same for the tan, negative pi 2 and pi 2. Okay, that makes sense. So within negative 90 and 90 degrees for sine and tan, so it's like a 180 kind of view. But for cos, it's between 0 and 180. So it's still a 180 view, but it's different quadrants. If you think back to the unit circle and recall that we think of cosine as the horizontal axis. Oh, and then sine is the vertical. Yeah, okay, that makes sense. Then we can see that we'll cover all possible values of cosine in the upper half of the circle. That is exactly the same, the range given above for the inverse cosine. Likewise, since we think of sine as the vertical axis of the unit circle, we can see that we'll cover all possible values of sine in the right half of the unit circle. That is the range given above. Okay. For the tangent range, look back to the graph of the tangent function itself, and we'll see that one branch of the tangent is covered in the range given above, so that is the range that we'll use for inverse tangent. Note as well that we don't include the endpoints in the range for inverse tangent, since tangent does not exist there. I'm not sure if I understand that. Note as well that we don't include the endpoints in the range for inverse tangent, since tangent does not exist there. Okay, I don't really understand that, but so if we can remember these rules, we will be able to determine the remaining angle in 0 to pi. That also works for each solution. As a final quick topic, let's note that it will on occasion be useful to remember the decimal representations of some basic angles. So here they are. Okay. Okay, I'm not gonna, I can see where they come from, but yeah. Using these angles, we can quickly see that cos of -1, 3 pi over 4 must be in the first quadrant, since 0.7227 is between 0 and 1.5. True. This will be of great help when we determine the following angles, or determine the remaining angles. So once again, we can't stress enough that calculators are great tools that can be of tremendous help to us, but if you don't understand how they work, you will often get answers to the problems wrong. So with that out of the way, let's take a look at our first problem. Oh man, 9 examples, huh? This might take us to the end of the stream, dude. Let me pull up my calculator for the first time in a while. Let's see. How do I show it on stream? I had it before. Oh wait, it's because it's the bottom here. There we go. Perfect. So, for cos t, I'll write this down. Example 1. We got 4 cos t equals 3. On -8, 10. That's a weird interval. So cos t equals 3/4. So we can find the inverse. 3/4 equals t. Alright. So that seems easy enough. Second cos 3 divided by 4. 0.7227. Let's see. Oh wait, we're finding all the hold up, Hyde. We still gotta do the thing though, because there's different solutions you can find. So 0.7227 plus 2 pi n again. Is this the same process? 0.7227 plus 2 pi 1. Make sure I'm in radian. 0.7227 plus 2 pi mode radian. Okay, so that gives 7 point, a lot of tabs open. 7.0058. 7.058. So this is one of them. This is another. 0.7227 plus 2 pi 2. So we got 0.7227 plus 2 plus 4 pi. and that's over. So that's 13.2891. And that is greater than 8, so it can't be the answer. Or, yeah, it's greater than 8. T does not equal that. T equals this. T equals that. Should probably have circled this one, but screw it, dude. 0.7227 plus or minus 2 pi. 0.7227 minus 2 pi. So we got negative 5.560. It's less than 8. Or wait, what's the interval? Negative 8. Oh wait, this has to be less than 10 up here. I got it mixed up. Still the same solutions, but yeah, so because this is greater than 10, it doesn't work. Not because it's greater than 8. For this, it's got to be less than 8. Negative 8, I mean. Or wait, greater than negative 8. Jeez. Oh, and it is. So it's one of the solutions. T equals 0.7227 plus 2 pi. What would be negative 2? Yeah, I guess I did negative 1 the first time. 0.7227 plus minus 2 pi. Oops, I don't know why I did that. .7227 minus 2 pi. Or wait, I just did the same thing again. 0.7227 minus 4 pi, I mean. 4. And that is negative 11.844 4. Oops, I did 3 decimal places up here. My bad. I'll have to go back. 8.437 is less. Wait. Yeah, less than negative 8. So T does not equal this. So how do I find this one? 0.7227 minus 2 pi. What? Give me an error. 0.7227 minus 2 pi. 5604. Okay. That's in 4, that's in 4. So I got 3. I got 3 solutions to this. So does he want these in, does he want us to convert this from decimal to, well, it's still in radian, but this is the other way of writing it. I don't know. I want to be able to do that. Okay, the first step here is identical to the problems in the previous section. First need to isolate the cosine on one side by itself, and then use our calculator to get the first answer. So cos t equals 3/4. T equals inverse cos 3/4, 0.7227. Okay, so this is the one we were using above in the opening discussion of this section. At the time we mentioned that there were an infinite number of answers and that we'd be seeing how to find them later. Well, that time is now. Oh yeah. First, let's take a look at the unit circle for this example. So 0.7227 is right here. Yeah, and if you reflect it across the x-axis, you get that it has to be this point over here. Yeah, because if you say all students take calculus, C cosine is positive down here, because it's a positive, what is this? Positive coordinate, I don't know, positive value. So it's cosine's positive here, you flip it, and yeah, okay. The angle that we've found is shown on the circle, as well as the other angle that we know should also be an answer. Finding this angle here is just as easy as in the previous section. Since the line segment in the first quadrant forms an angle of 0.7227 radians with the positive x-axis, then so does the line segment in the fourth quadrant. This means that we can use either negative 0.7227 as the second angle, or 2 pi minus negative 0.7227 equals 5.5605. Okay. Was that one of my answers? No. I got a negative. I do get how you got that though, because you're finding the reference angle. So you're only finding this part right here for the angle, and you know it's the same as this, which is 0.7227. So you take the whole circle minus 0.7227, you get just this. Oh, that we can use either negative 0.7227. Wait, negative. Oh, like, yeah, okay. Or 5.5605. How didn't I get that the way I did it? I did this answer minus 2 pi, okay. I'll keep reading. Which you use depends on which you prefer. We'll pretty much always use the positive angle to avoid the possibility that we'll lose the minus sign. Okay. So all possible solutions, ignoring the interval for a second, are then 0.7227 plus 2 pi n. Or, oh, that's how we found there's a whole other set of solutions you can use. Plug values of n, here's the ones that work. So I found just one set of solutions pretty much. Yeah. Negative 7.0059. Did I not round this? Whoops. Negative 5.6. Alright, I got the first set right, but I was missing a whole other set of solutions because I didn't draw out the unit circle and like think about it kind of. So if we know 7.227 is like here, then, and it's a cosine, and it's positive, so it has to be, the other solution has to be down here. And then you're only trying to find this in radians. Or really you're trying to find everything but this, because you're finding like You know. So you would take a full rotation minus 0.7227 you get 5.560 crap 5.5 wait I was right 604 605. Okay, so that's this rotation to the reference angle. And 0.7227 is this. So you can write that as that plus 2 pi n 5.5605 plus 2 pi 1 5.5605 plus let me write down 5.5605 plus 2 pi. So I don't just write down the answer. So T equals 11.8437. I think that's over the interval, right? So it doesn't work. Yeah. So that's greater than 10, so it doesn't equal T. 2 pi, or wait, 5.5605 minus 2 pi 1. Is that equal? We got negative 0.7227. Negative, oh wait, why am I plugging that in? Okay, that's one of the answers. Because it is greater than negative 8. So 5.5605 minus 2 pi 2. 5.5605 minus 4 pi. 5.5605 minus 4 pi. We got negative 7.0059. Okay. And that is greater than negative 8, one of the solutions. Last one should go over. 5.5605 minus 2 pi 3. 5.5605 minus 6 pi equals 5.5605 minus 6 pi negative 13.2891. It's not an answer because it's greater than, it's less than negative 8. So solutions should be 7.0059, negative 7.0059, negative 5.5604, I said 04, negative 0.7227, positive 0.7227, 5.5605. Oh wait, that's the original. I forgot to circle that. So like that. 7.0059. It's 5.8. Alright, whatever. Close enough. Forgot the round in some places. Did I? No, I did that. Wait, this is 1.4. What did I do? Note that we had a choice of angles to use for the second angle in the previous example. The choice of angles there will also affect the values of n that we'll need to use to get all the solutions. In the end, regardless of the angle chosen, we'll get the same list of solutions. But the values of n that give these solutions will be different depending on our choice. Okay. Also in the above example, we put a little more explanation than we'll show in the remaining examples in this section to remind you how these work. Okay. So these have different values of n if you we had a choice of angles to use for the second angle. And if you use negative 0.7227, you'd have to use different values of n, really. I don't know, I have to work through it, but so we're on example 2. Solve negative 10 cos 3t equals 7 on negative 2, 5. Okay, so we got cos 3t equals negative 7/10. So cos, inverse cos negative 7 over t, negative 7 over 10 equals 3t. So then I'll use the calculator to find that out. Negative 7 over 10. So we got 2.3462 equals 3t divided by 3. Two 0.3462 divided by 3. 0.7821. Okay. So if we know that should be around the 0.7227, because what's 90 degrees in radians in decimal form? 1.5708. So it's definitely in the first quadrant. And is this sine? Or no, this is cosine, isn't it? Yeah, this is cosine. So draw out the unit circle. It's going to be in the first quadrant again. Pretty much the same thing. That was a long line. So something like this. And then draw a straight line down, because cosine is positive in these two quadrants. Since this is a positive number, it has to be in these two quadrants. We're trying to find the rotation. Okay, so this is the rotation, or this is the angle 0.7821, and we're trying to find the whole thing down to here, down to this reference angle. I don't want a negative here. I could use it, but so since this is the same thing right here, I'm trying to find everything else. So we do a rotation 2 pi minus 0.7821, and that'll give the big one. Should be similar to the last one. So we got 2 pi minus 0.7821. So 5.5011. So before I find all the, well, let me write it out first. 0.7821 plus 2 pi n, 5.501, 5.5011, yeah, plus 2 pi n. I want to make sure that I rounded right, because he could have done it, he could have plugged the actual value of this, and then divided by 3 and got something different. I would have thrown off everything. So just to make sure. Okay, so we got, he divided 2.3462 divided by 3, which I think was what I did. 2.3462 divided by 3. .7821 plus 2 pi. Oh, you gotta divide that by 3. Okay. True. Forgot to do that. Man, that's easy to do. And I didn't divide this by 3 either, did I? Yeah, I gotta divide this by 3. So 5.5011 divided by 3. Crap, I hate when it does it. 5.5011 divided by 3. Okay, that didn't give me the right answer, so. Wait, backwards? What? Huh? What is all this? This is crazy. Oh, because it's the original that we plugged in, -7/10. It's a negative, so this actually gets flipped. Okay, that screws everything up. Draw this again. I'm confused there because 0 point whatever is 7 whatever is positive. Okay, so I'll just read it. So let's first get the inverse cosine portion taken care of. Okay, that's the same thing I did. Don't forget, we still need the 3. Now let's take a quick look at the circle for this problem. As we can see, the angle 2.346. Oh, because we're just looking at it as the unit circle, 2.4362, whatever. That's in this quadrant right here. Because if you look at that list he showed, pi, full rotation, 180, or half rotation, 3.1 whatever. The answer, 2.34, would be in the middle somewhere around here. Which means, and that makes sense because the original is negative. So this is really bad, but. So from here to here is 2 point blah blah blah. So we're gonna take that and we're gonna be like pi plus pi, wait, no. Got it mixed up. Pi minus, wait. Yeah, it'd be pi minus 2.3462. Because this is the same thing. Take 180 minus this number So then you're going to get like this hole right here, which is the same thing as this. So pi minus 2.3462. Minus 2.3462. We get 0.795 So both of these got to be divided by 3. So I'll just save that for after. Move this up. Yeah, so 0.7954 is what I got after subtracting. So I'm gonna flip these so it's easier for me to remember. Actually, it looks bad. Hold on. I'll just like separate them. Zero 0.7954 t equals or 3t 3t equals plus 2 pi n plus 2 pi n. So yeah, that should make sense. Let's see. 3t equals 2.3462 plus 2 pi n. 3.970. Oh, wait. Hold on. I only found this little angle right here. I gotta add that on to 2.3462. Was there an easier way of doing that? I can't think of it right now, but I'm sure there is. So 0.7954 plus 2.3462, 3.1416. Is that it? Doesn't sound like it. No. Okay, what are we doing here? He did 2 pi minus 2.3462. So he took a full rotation minus this. Why? I thought we were only finding to here. Because if you're doing that, you're finding like to here. Right? It's confusing. Yeah, how's this in the third quadrant? Or wait, no, it is the third quadrant. Okay, that makes sense. That makes sense. But the way he got it though, so he takes 360 basically, minus something in the second quadrant. So that'd be like finding the whole rest of the circle. I don't understand that. Because 2 pi is 6.2823. Wait a minute. Okay, what if I did... What if pi... Now I'm gonna do it in a weird way. That's gonna be like stupid. Pi minus 2.3462. So this is the angle of that triangle. So 0.7953 I mean. Plus pi. Yeah, that gives the answer. So wait. Why can't I like wrap my head around like the 2 pi minus 2 point whatever thing? It just doesn't make sense to me. Because when you be getting this whole angle here, like what? Two pi minus this. Bruh. Oh, wait a minute. Oh, wait. So from here, from starting 0 to this angle, it makes like a... Hold on. That's like all of this, right? And if you take 2 pi, the entire thing, and you subtract off this part here, that's basically the same as just subtracting this part off. So you get the same thing. So 2 pi, this is 2 pi, minus this angle. You're left with the rest of this, which is like the same thing as this. Okay. I don't know why that's like so confusing for me. So 3t 3.936. What is this pen right here? 7, I mean. 3.93. Oh wait, 3.936. 370. 3.9370. Yeah. And then divide by 3. T equals 2.3462 divided by 3. 0.7821 plus 2 pi n over 3. So that's the first answer. Divide by 3, divide by 3, divide by 3. T equals 3.9370 divided by 3, 1.3123 plus 2 pi n over 3. So that's the second answer. And then t equals 0.7821 plus 2 pi 1 divided by 3. 0.7821 plus 2 pi divided by 3 plus 2.0944. 0.944. Okay. 0.7821 plus 2.0944. Get 2.8765. 2.8765. And is that, what's the interval? -2 and 5. Well, that's less than 5, so we're good. Alright, finish this up. 2 pi times 2 over 3. 0.7821 plus 2 pi times 2 divided by 3. You know what? Okay, just here. 4 pi divided by 3. It's 4 pi divided by 3. 0.7821 plus 4.1887. 1888, man. 4.1888 plus 0.7821. You get 4.9709. Less than 5 it is. So that's the solution. Next one, 0.7821 plus 2 pi times 3 over 3. The 3's cancel out. 0.7821 plus 2 pi. And do we do this one because it's just it's a full rotation. Wait a minute. We'll still do it. Yeah, what's it equal? Let's see. 0.7821 plus 2 pi 7.0653, and that's not an answer, so because it's greater than 5. So I found all the answers for positive in the positive direction for 0.7821. So I gotta find negative and positive and negative for 1.3123. So, all right. Save. So 0.7821, I think, plus 2 pi negative 1 over 3, 0.7821 minus 2 pi over 3. What's it equal? .7821 minus 2 pi over 3. I'm afraid I wrote that wrong. With PEMDAS it should have been fine, but who knows. Minus 2 pi divided by 3. Okay, it's the same. Negative 1.3123. And what's it have to be in? And it's greater than negative 2. So it works. Next. 0.7821 plus 2 pi negative 2 over 3. 0.7821 minus 4 pi over 3. 0.7821 minus 4 pi over 3. Negative 3.4066. And that is less than negative 2. So t does not equal It's not right. Next. 1.312, okay. Let me save this first. T equals 1.312 plus 2 pi n over 3. Uh, 1.3123 plus 2 pi 1 over 3. 1.3123 plus 2 pi over 3. Plus 2 pi over 3. Correct. 1.3123 plus 2 pi over 3. 3.4067. And I think it has to be less than 5, right? Yeah. It's less than 5, so t equals, it's one of the answers. T equals 1.3123 plus 2 pi plus 2 pi negative 2, no, 2. Forgot I'm not on negatives yet. 3. 1.3123 plus 4 pi over 3 equals 1.3123 plus 4 pi over 3. Dude, I hate when it does that, it's so annoying. 1.3123 plus 4 pi over 3. 5.5011. And that's greater than 5, so that can't be t. 1.3123 plus 2 pi negative 1 over 3. 1.3123 minus 2 pi over 3. The answer is 1.3123 minus 2 pi over 3. So we got negative 0.7820. Oh wait, it's 21. 0.7821. Has to be greater than what? Negative 2? It's greater than negative 2, so it's an answer. 1.3123 plus 2 pi negative 2 over 3. 1.3123 minus 4 pi over 3. 1.3123 minus 4 pi over 3. Nick's playing Pizza Tower, nice. Negative 2.8765. And that is greater, it's less than negative 2. So it can't be an answer. And that's all of them, or should be. So, the answer should be not 2.8765, negative 0.7821, 3.4067, negative 1.3123, 4.9709, 2.8765, 1.3123, 0.7821. I think I got all of them. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah. We've done a couple of basic problems with cosines. Now let's take a look at how solving equations with sine work. You know what, screw it, let's go to 3 hours. Let's do it. So example 3. Got 6 sine x over 2 equals 1 on negative 20, 30. So first, sine x over 2 equals 1, 6. Sine 1 over 6 equals, or sine, inverse sine 1 over 6 equals x over 2. X over 2 equals 1 over 6. 0.1674. 0.1674 times 2. X equals 0.1674 times 2. 0.3348. Okay. Actually, you know what? First, before I multiply by 2, I just want to have this. Right. So this is without manipulating anything. 0.1674, where would that be? Definitely first quadrant, for sure. Whoa. So it's really 0.1674. It's gonna be like here. And then sine, okay, so sine is positive. Okay, sine's positive, second quadrant. So we gotta find the one over here. You can find that by doing pi minus 0.1674, probably. We're taking the whole thing here minus like a triangle. So that should get us to here. So we got pi minus 0.1674. $2.974 2. 2.9742. So we got x over 2. It can equal 0.1674. But it can also equal 2.9742. Multiply by 2 to both. 0.1674 times 2. 0.3348 plus 2 pi n. So that's one of the answers. X equals 2.9742 times 2, 5.9484 plus 2 pi n. So that's one of the answers. So yeah, I'm gonna check these before I start plugging in numbers, because I don't want to plug in like 100 numbers and then they're wrong. So let's first get the calculator. Probably let the calculator work out. Wait. Oh, let's get the calculator work out of the way, since that isn't where the difference comes into play. Okay, so he got 0.1674, which is what I got. Unit circle. Okay, same. Pretty much the same unit circle drawing. To find the second angle in this case, we can notice that the line in the first quadrant makes an angle of 0.1674 with the positive x-axis. And so the angle in the second quadrant will then make an angle of 0.1674 with the negative x-axis. So if we start at the positive x-axis, we rotate a half revolution, and then back off 0.1674. Yep. Therefore the angle is pi minus 0.1674. That's exactly what I did, I'm pretty sure. So it equals 2.9742. Yep. Here's the rest of the solution for this example. We're going to assume from this point on that you can do this work without much explanation. So x over 2 equals 0.1674 plus 2 pi n. I forgot to divide the 2 pi n by 2. Man, that's a tough one. So then this would just be pi n. Alright, good thing I checked. Plus 2 pi n over 2. Wait, multiply it by 2, not even divide. Crap. Alright. Yeah, good thing I didn't start plugging in numbers. So we got plus 2 pi n times 2. So we got 4 plus 4 pi n. Looks terrible. Four pi n plus 2 pi n times 2. So we got 0.3348 plus 4 pi 1. 0.3348 plus 4 pi. So we got x equals 0.3348 plus 4 pi. 12.9012. And what's the thing? 30. So it's less than 30. So we're good. 0.3348 plus 4 pi times 2, 0.3348 plus 8 pi, 0, I'll get the answer now, 0.3348 plus 8 pi, 25.4675. And that's less than 30, so it's an answer. Zero point 3.348 plus 4 pi 3, 0.3348 plus 12 pi, 0.3348 plus 12 pi, 38.0339, and that is greater than 30, so it doesn't work. Next, 0.3348 plus 4 pi times -1, 0.3348 plus minus 4 pi, 0.3348 minus 4 pi, -12.2316. That is greater than -20, so it works. X equals 0.3348 plus 4 pi -2, 0.3348 minus 8 pi. X probably does not equal 0.3348 minus 8 pi -24.7979, because it is greater than, or no, less than -20, so it's not an answer. Alright, next was the other one. X equals 5.9484 plus 4 pi, and then start plugging in. 5.9484 plus 4 pi. X equals 5.9484 plus 4 pi, 18.5148, and that works because it is greater than or less than 30. 5.9484 plus 4 pi 2, 5.9484 plus 8 pi, so it's probably not going to work. 5.9484 plus 8 pi, 31.0811, and that is greater than 30, so X does not equal this. Alright, just the negatives left for this one. 5.9484 plus 4 pi -1, 5.9484 minus, minus 4 pi, that equals 5.9484 minus 4 pi negative 6.617 or 180. And that works because it is greater than I think negative 10 is the no negative 20. Jeez. 5.9484 minus or plus 4 pi minus 2. 5.9484 minus 8 pi plug that in. 5.9484 minus 8 pi negative 19.1844 is greater than negative 20, so it works. We've got x equals, not x equals, but 5.9484 minus 4 pi negative 3 should be where it stops, hopefully. 5.9484 minus 12 pi 5.9484 minus 12 pi negative 31.7507. Definitely smaller than negative 20, so it's not equal to x. Okay, that should be everything. So let's check. So we got negative 19.1844, negative 6.6180, 18.5148, negative 12.2316, 25.4675, 12.9012, 5.9484, 0.3348. And how many, because those were like way out of order. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, we're good. Example 4. I see single solution. I'm going in for this. I was gonna stop, but I can get that done. 3 sine 5z equals negative 2 on 0, 1. So we got sine 5z equals negative 2/3. Inverse sine of negative 2/3 equals 5z. Find the inverse sine. Negative 2 divided by 3. So we got negative 0.7, negative 0.7297. 0.7297. Move this over. And that equals 5z. Okay, so this is sine to begin with. So we're going to make the unit circle. And let's see. So it's negative 0.7297. So 0.7297 is going to be in the first quadrant for sure. But opposite of that, it's going to be about here. Okay. But it's originally positive. Does that matter? No, because there's a variable, so it, okay. Crap. So, yeah, if we did 2 pi minus, whoops, minus 0.7297. Okay, so this is 5. This whole thing right here is 5.5535. 5.5535. And we know sine has to be negative. So where else is sine negative? So it'd be negative over here too. That's terrible. So if I do alright, wait. I'll do this in a way that makes sense. 2 pi minus 5 point, I should get the same thing I had originally. 5535. So 0.7297. 0.7297. That's like this triangle right here. It's also this triangle over here. So if I add 180 or pi, this rotation should be 3.8713. Again, could be way off, but so let's see. So from there I want to divide by 5. So 5z equals 5.5535, and 5z equals 3.8713. Oh, plus, I didn't forget this time, plus 2 pi n. Yeah, just plus 2 pi n, plus 2 pi n. Divide by 5. Z equals 5.5535 divided by 5. It's a lot of 5s. 1.1107 plus 2 pi n over 5. So this would be one of them, or no, it wouldn't. This wouldn't even, it's not between 0 and 1. Alright, that was the, it's not the interval. Yeah. Z equals 3.8 3.8713 divided by 5. 0.7743 plus 2 pi n over 5. So this would be one of the solutions. And it said only one solution, so I'm gonna guess. Hopefully I got it right, that's the only one. But if I didn't know there was one solution, 0.7743 plus 2 pi 1 over 5. Z equals 0.7743 plus 2 pi over 5. It's 2.030, no, 0.31, 0.309. Which is greater than 1, so z does not equal this. So z equals 0.7743 plus 2 pi negative 1, 5. 0.7743 minus 2 pi over 5. So we get z probably does not equal 0.7743 minus 2 pi, what did I even type? Minus 2 pi over 5. Negative 0.4823. Yeah, so, which is less than 0. So this is not the answer. So hopefully you got that right. Let's check. You should be getting pretty good at these by now, so we won't be putting much explanation in for this one. I hope I'm getting good at these. Here we go. Sine 5z equals negative 2/3. Negative 2/3, okay. Yep. 5z equals inverse sine. Negative 2/3, that's what I did. Equals negative 0.7297. Yep. So he puts that on the unit circle. Finds negative 0.297. Okay, with this one we're going to do a little more work than with the others. For the first angle, we could use the answer our calculator gave us. However, it's easy to lose minus sign, so we'll instead use 2 pi minus 0.7297 equals 5.5535. Again, there's no reason to this other than I'll worry about losing the minus sign and the calculator answer. If you would like to use the calculator answer, you're more than welcome to. For the second angle, we'll note that the lines in the third and fourth quadrant make an angle of 0.7297 with the x-axis. Yeah, true. So if we start at the positive x-axis and rotate a half revolution around, and then add on 0.7297 for the second angle, therefore the second angle is, that's exactly what I did, nice. We get the same answer though. 3.8713. Yep. So here's the rest of the work. Plus 2 pi n, divide by 5. So should have z equals 1.1107 plus 2 pi n over 5. And then 0.7743 plus 2 pi n over 5. So the only answer is 0.7743. So in this case we get a single solution of 0.7743. Note that in the previous example, we only got a single solution. This happens on occasion, so don't be worried about it. Also note that it was the second angle that gave this solution, and so if we just relied on our calculator without worrying about other angles, we would not have gotten this solution. Again, it can't be stressed enough that while calculators are a great tool, if we don't understand how to correctly interpret / use the result, we can and often will get the solution wrong. To this point, we've only worked examples involving sine and cosine. Let's now work a couple of examples that involve other trig functions to see how they work. Yeah, let's not do that today. Wow, this section was a lot longer than I thought. For sure. So yeah, I'll stop there today. What's coming up after this? Calculator part 2. I'm sure that'll be just as long, but with less examples, so guess not as long. Exponential functions. This doesn't seem too hard. Logarithm functions. I think I'm decent at logarithms. Exponential and logarithm equations. Probably shouldn't be too bad. Common graphs. Some of these I could definitely do some review on. So what day is it today? June 6th? Okay. I could definitely get this review done by June 10th. Hopefully before. So yep, that's where I'm gonna end today. How long did I stream? 3 hours, 8 minutes, almost 9. That's kinda crazy.